Good morning. My name is Daniel Loeffler. I am with Catalytic, a chemical research company in Mountain View, California. And today we are going to talk about the role of mass transfer in heterogeneous catalytic reactions. Heterogeneous systems have more than one phase, and the characteristic of these systems is that there are marked local variations in compositions in the reaction mixture. As a result, not all reactive molecules are available for chemical reaction. Specifically, we are going to talk about heterogeneous reaction at a catalytic surface. And we are going to consider the ideal reaction. A in the gas phase goes to products in the gas phase also. In order for this reaction to go on, the reactant A has to reach the surface of the solid catalyst. It has to react to products P on this surface, and then it desorbs and returns to the main gas phase as product P. Now, the conversion can only take place when species A is transferred to the interface where the reaction proceeds. And therefore, the rate of mass transfer from the bulk gas to the surface will influence the rate of conversion in the system. In general, when we have mass transfer with heterogeneous reaction, the course of the chemical reaction is described by a combination of chemical kinetics and mass transfer phenomena. This is chemical phenomena and physical phenomena. Mass transfer is a physical phenomena. The conversion rate expressions will account for the interaction between mass transfer and a chemical reaction. Again, in the case of heterogeneous catalysis, the reaction takes place on the surface of a catalyst, and these reactants are present in the fluid phase surrounding the catalyst. Our objective today will be to investigate the interplay between the true chemical reaction rate and physical transport phenomena. We will try to suggest ways to identify those effects and to avoid them in the laboratory, because when we work in the laboratory, we always want to see the true chemical reaction rate, and we will try to avoid any physical mass transfer limitations that may hinder our observation of the true chemical reaction rate. Okay, let's look in some detail at what happens when we have a reactant in the gas phase and the reaction occurs on the surface of a solid catalyst. Let's take a look at this drawing here. Here we have the gas phase in which the main flow of the reactant is occurring, and we have a solid catalyst on which surface the reaction takes place. Now, let's assume we have here reactant gas A. In order for the reaction to take place, the reactant species A has to reach the surface of the catalyst. We will assume that there is a resistance to mass transfer which is concentrated on a film, in a film of thickness delta, which is next to the surface of the solid. So reactant A has to overcome this resistance, get to the surface of the solid. So the first point that we have here is mass transfer of reactants from the main flow to the external surface of the particle. Then this reactant A has to reach the inside of the pore in which, we are assuming that the catalyst is a porous solid, so the reactant has to get into the pore. And once it is in the pore, it has to adsorb on the surface of the solid. Once it is adsorbed, it will react. And then, once it reacted, it desorbs to the interior of the pore, and it has to diffuse to the surface of the catalyst and then through the boundary layer to the main to into the bulk gas. So all these 7 steps have to occur for the reaction to take place. And let's recap. We have mass transfer of reactants from the main flow to the external surface of the particle. We have transport of reactants by the fusional process through the pores into the particle. We have adsorption of reactants on the internal catalyst surface. We have chemical reaction in the adsorbed state. We have desorption of products. Then we have transport of products by the fusional process out of the particle. And finally, mass transfer of products from the external surface into the main flow. Now, in the case of a non-porous particle, if the reaction occurs on the external surface of the catalyst, like here, of course, steps 2 and 6 will not happen. I mean, diffusion into the pore and diffusion out of the pore will not happen because there is no pore. Now, let's see. The rate of each step can be written as a rate will be equal to a driving force divided the resistance. In the steady state, the rate of all steps 1 through 7 should be the same. Therefore, there are no slow and fast steps. Here we have a process which occurs in series. Each step has to occur, I mean, the reactant has to go to the surface of the catalyst, it has to react there, and then it has to diffuse back to the main flow. Each of these steps has to proceed with the same rate. So this is a series process, and there are no fast and slow steps. If the rate of each of one of these steps would be different from another, there would be accumulation of matter at some point in the catalyst. We are assuming steady state. The assumption of steady state implies that there are no slow and fast steps. All steps proceed with the same rate. So what there is steps with high and low resistances. If we have a step with a high resistance, that step will have a large driving force. If the resistance is low, the driving force will be small. And let me clarify this point a little bit because I believe it is important. Let's assume this is the surface of the catalyst, and this is the film in which we assume the resistance to mass transfer to be concentrated. We have reactant A, and this reactant A will diffuse to the surface with a flow rate that we call NA. This will be mole per square centimeter per second. And this reactant A is in the bulk phase, bulk gas phase with a partial pressure PA. And here, right next to the surface, we will have a partial pressure PA sub S. So the driving force, NA, will be equal to a driving force. The driving force will be PA minus PAS. And the resistance will be 1, we will call it 1 over kg. Or, okay, so if this resistance is large, this driving force will also be large. If the resistance is small, this driving force will be small. If the resistance is small, that means that the partial pressure is uniform throughout this film. Otherwise, we will have a decay in the partial pressure of A, PA, and this is distance through the film. This should be a straight line. Now, Kg is the diffusion coefficient of a species species A in this boundary in this film divided the film thickness. Now, the use of the porous catalyst is maximum when the entire internal surface is accessible to reactants. Therefore, we would like to have as low physical resistance as possible in order to use all the internal surface of the catalyst for the chemical reaction. If the physical resistances are high, the only surface which will be available for reaction will be the internal surface, the external surface. If we go back to this drawing, we see that if the resistance for mass transfer is high, the reactant A will not reach into the pore. It will only react on the external surface of the catalyst. And we lose all this surface for chemical reaction. Now, in order to analyze in quantitative detail the rate process for reaction with diffusion in a pore, we need to know the diffusivities in the gas phase and in the pore. Now, the diffusivities in the pores, or the internal diffusivities, will depend on pore size distribution, on the connection between pores. This is the so-called texture of the catalyst, the internal structure of the catalyst. And it will depend also on the diffusion mechanism. The diffusion mechanism in the pore can be a normal molecular diffusion, Knudsen diffusion, or migration in the adsorbed state, also called surface diffusion. Let me clarify this a little bit. If we have a catalyst pore like this, a gas molecule in this pore will diffuse. I mean, we will assume well, the gas molecule in the pore can diffuse by a normal molecular diffusion, that is by multiple collisions with other molecules. But in general, these pores, the diameter of this pore is less than the mean free path of the gas molecule. If the diameter of the pore is smaller than the mean free path of a gas molecule, the diffusion in the pore will occur by the so-called Knudsen diffusion. That is, that the molecule makes multiple collisions with the surface of the catalyst. That is, before having a molecule-to-molecule collision or a particle-particle collision, we will have a particle wall collision. This is the so-called Knudsen diffusion. The other mechanism that I mentioned, migration in the adsorbed state, indicates that the molecule, upon collision with the surface, may adsorb and then migrate in the adsorbed state, right, on the surface. So the three mechanisms that we may have for diffusion in a pore is normal molecular diffusion in the gas phase, Knudsen diffusion by multiple collisions with the walls, or migration on the surface of the catalyst. In general, the internal diffusion coefficient, that is the diffusion inside the pore, may be 10 to 100 times smaller than the molecular diffusion coefficient outside in the gas phase outside the catalyst. Okay, if we go back to our series of steps that the reactant has to follow in order to be converted into products, we may remember that we had the mass transfer from the main flow into the surface of the particle, transport through the pores, and now we have the particle. We have our gas molecule next to the surface of the catalyst, and three more steps have to take place, namely adsorption of reactants on the internal surface, chemical reaction, and desorption of products. Now, usually all these three steps cannot be analyzed independently, and the expression for the kinetics for the surface reaction contains all these three steps: adsorption, chemical reaction, and desorption. And that's why expressions for heterogeneous chemical reactions are usually quite complex. We will try to find an expression for a chemical reaction on a surface following the treatment proposed 70 or 80 years ago by Langmuir and then popularized by Hinchelwood in the late 20s. We first assume that the reaction is a unimolecular irreversible reaction of the kind A goes to products. And there is a surface rate for this. There is a rate for this surface reaction that we will call KRAS. This AS is a surface concentration in molecules per square centimeters. This is the concentration of the adsorbed molecules. Now, the concentration of the adsorbed molecules is difficult to measure. Therefore, we usually use a relation between gas phase concentration and surface concentration. This relation is written in this way. The concentration on the surface will be a maximum concentration on the surface times theta A, where theta is a parameter that varies between 0 and 1. This is also called the coverage of the fractional coverage of the surface, and an expression for this surface coverage will include the adsorption and desorption rates. We will try to find that expression by writing the rate of adsorption equal to Ka times the partial pressure of the gas times the fraction of the surface which is available for adsorption. That fraction of the surface will be 1 minus the fraction covered with species A minus the fraction covered with species P. Now, this will be the rate of adsorption. In order for a molecule to get to the surface, it has to find a portion of the surface available for adsorption. That portion of the surface will be 1 minus the surface which is covered with molecules A minus the surface which is covered with molecules P. So that will be the rate of adsorption. Now, the rate of desorption will be proportional to the fraction of the surface which is covered with species A. In the steady state, when there is no accumulation of matter in the surface or in the gas phase, the rate of adsorption should be equal to the rate of desorption. Well, if we do some algebra with these two equations, we get two expressions like this. That gives us the coverage of the surface as a function of the partial pressure of the reactant and the partial pressure of the products. This K here is the ratio of adsorption and desorption rate constants. Well, finally, we can write an expression for the surface reaction rate as a function of the partial pressures of reactants and products. This rate will be Kr, as we have seen before, times the maximum coverage possible on the surface times this equilibrium constant times the pressure divided 1 plus Ka Pa Kp Pp. So here we can see that if the partial pressure of the product is too high, or the adsorption, the equilibrium constant for adsorption of products is too high, the products may reduce the rate of reaction. I mean, as we build up products, the reaction rate may be reduced by the presence of these products that occupy sites on the surface of the catalyst. Now, well, this is the same rate expression that we have written before. Now, let's see what happens if we have, KAPA plus KPPP is small. I mean, these two terms are much smaller than 1. Well, in this case, if these two terms are much smaller than 1, we will have that the rate will be just proportional to the partial pressure of A in the gas phase. Therefore, we have a first order reaction in partial pressure of A. And we can lump all these three constants into a rate constant K. And in this way, we obtained a first order rate constant in the partial pressure of A for our system. This K includes the rate parameters for adsorption and desorption. Now, one point that I want to make clear is that the partial pressures PA and PP, sorry, PA and PP, are those next to the surface and are in equilibrium with the surface concentrations of species A and P. This means that if we have our solid surface, this is our solid surface, and we have the main flow here, and this is PA here, the partial pressure which will be at equilibrium with the surface will be a PAS right here next to the surface. This will be in equilibrium with the surface, not this one if we have mass transfer resistances here. So, in fact, the partial pressure that should be written in here for A and here for P is the pressure which is right next to the surface in equilibrium with the surface. When we have mass transfer resistance, this pressure will be different from this. And that's what I've written here. When mass transfer resistance are significant, PA and PP will differ from those partial pressures measured in the bulk gas. Well, now we have all the elements to look at the complete picture of mass transfer to a catalytic surface. We will, for simplicity, assume that we have a non-porous particle, so we are going to look at heterogeneous reaction at an external surface. That is, only the external surface of the catalyst is available. We assume that there is no pores. And now the resistance for transport of A and P are the same. We will assume this, that we will assume that the resistance for A and P for transport of A and P are the same, and we can write Kg equal the diffusion coefficient, the same for both species, divided a film thickness. For step 1, we can write that the rate of mass transfer to the surface will be equal to Kg times a driving force PA minus PAS. We have seen before for steps 3, 4, and 5, we can write that the rate will be equal to K times PAS. And finally, for the desorption of products, we can write a rate expression NP equal to Kg PPS minus PP. Now, at the steady state, we have that the rates of these three steps will be the same, and A will be equal to RA equal to MP. If this was not the case, there would be accumulation of matter at some point in the system. So from here, we can write this. The rate will be Kg PA minus PAS equal to K PAS. And after some algebra on this expression, we can write that the rate will be equal to the partial pressure of A in the main gas, the main gas phase, main gas flow, divided 1 over Kg plus 1 over K. Now, you see, we wrote this, we went through this algebra in order to get a rate expression function of the pressure of A, the partial pressure of A in the main gas flow, because this is the partial pressure that we can easily measure. this partial pressure can be a partial pressure that we measure with our instruments in the lab. It is very difficult to measure PAS, but it's easy to measure this. So that's why we got this equation. Now, we may also write, we may write RA equal to K prime PA, and this K will lump all these two rate constants in this way. So now we will we can plot this K, the K that we have here, as a function of 1 over T in an Arrhenius type plot. Now, let's look at some extreme cases. Let's assume the temperature is very high, so we are working here. If the temperature is high, this K will be large. This will be an Arrhenius type expression. And this K will be equal to a pre-exponential times e to the minus e over RT. As T increases, this K will increase. If this K is large, 1 over K will be small. Therefore, this K here, the reaction rate, will be proportional to this reaction rate will be proportional to kg PA. We will have a system controlled by mass transfer effects. The chemical reaction rate will be not important. And we are here. Here is the mass transfer control regime. And this Arrhenius plot will have a slope, a small slope, because this Kg, which you may remember is d over film thickness, will be weakly dependent upon temperature. The diffusion coefficient is weakly dependent on temperature. Therefore, in the mass transfer control regime, the slope of the Arrhenius plot is small. As temperature decreases, this rate constant will decrease. Therefore, 1 over K will become larger. And at some point in time, it will be large enough for K, the rate of the overall process, to be equal to 1 over K. This is times PA. This will be equal to K PA. And the reaction will be controlled by a chemical reaction. The process will be controlled by chemical reaction. Chemical reactions have activation energies larger than diffusion coefficients. Therefore, here, the slope of the Arrhenius plot will increase. Typically, the activation energy for the chemical control regime will be larger than 10 kilocalories per mole. Now, we can look at some real-life data. In this case, we have methane decomposition on tungsten. These are reaction rates in molecules per square centimeter per second. This is molecules of methane that decompose per square centimeter of tungsten per second as a function of reciprocal temperature. This is an Arrhenius plot. We can see that at low temperatures, we have a reasonably high activation energy, and the experimental data points align following a straight line. At high temperatures, the activation energy is much smaller, showing the diffusion controlled regime. I want also to point out the rates that we are measuring. These rates are between, this is 10 to the 20, and this is 10 to the 21 molecules per square centimeter per second. We will come back to these values in a while. Another well, we may define for this heterogeneous reaction an effectiveness factor as the ratio of the observed reaction rate divided the rate that would be observed if mass transfer resistance were not there. So we can write the rate, the observed reaction rate, as we did before, as PA divided 1 over kg plus 1 over k. And this whole thing divided the rate that we would observe if there were no mass transfer resistances as PA times a constant k. Okay, this can be written in like this. And we can see that the utilization of the surface will decrease as this factor increases. We may plot this to show this more easily. We may plot the log of n divided the log of kg over d. And this will be a plot, this will be 1 here, and this will be a plot like this. That means that as delta, the film thickness, increases, the utilization of the surface decreases. That is, the rate that we see will decrease. We can go back to this expression here. If this term increases, this ratio decreases. Therefore, as mass transfer resistance increases, the observed rate will decrease. And therefore, the surface will be less utilized than if we didn't have mass transfer diffusion, mass transfer resistances. Another effect that we observed when we have external mass transfer resistances is a decrease in the selectivity. Here we assume that we have a reaction of a kind A goes to P as before, as we had before, but now this product P reacts to make some undesirable product C. This is the product that we want. This is the product that we do not want. This is a very common example of reaction of these kinds are partial oxidations. For example, we may want to partially oxidize methane to methanol. This will be methane, this will be methanol, but methanol will react with oxygen and give CO2 that we do not want. So this is a reaction sequence in which we want the intermediate product, not the final product of the sequence. We may define selectivity as the rate of production of P divided the rate of conversion of A. And the rate, well, let's look at the drawing and see what this means, what will happen. Again, we have a solid surface. We will have a mass transfer resistance concentrated in a film of thickness delta. We will have our reactant A, which in order to react has to reach the surface, and we have A on the surface. This reactant A will react and make product P. Now this product P can go two ways. It can either desorb back to the main gas flow, or it may react to make the unwanted product C. And this product C in turn will desorb to the main gas flow. We will for simplicity, we will assume that the concentration of P here is very small, close to 0. And we can write then for the rate of production of P. Well, let's go back to the selectivity. The selectivity will be K1 PAS. This is the rate in which A reacts, minus the rate with which P reacts to C. The difference will be the rate of production of C. Back to this cartoon. The production of P, the P that will come this way, will be the amount of A that goes to P minus the P that goes to C. I mean, the balance will be the production of P. That's what we have here. This is the balance. Production of P will be the balance between what is converted from A and what P is converted into C. Then this is divided the conversion of A, which is K1 PAS. Now we can write also for the rate of production of P the rate with which P desorbs from the surface to the main gas flow, the rate for this step. The rate of conversion of A will be the rate in which product P is desorbed plus the rate in which product P is converted to unwanted product C. If we substitute these two terms into this expression, we get an expression for the selectivity, which looks like this. And when we plot this, we will have that selectivity will be 1. And well, this will be selectivity, and this will be K2 delta over T. This is a log-log plot. And the shape of this plot will be, as we have seen before, indicating that as the mass transfer resistance increases, the selectivity for the reaction decreases. The reason for this is that as the resistance for mass transfer increases, product P will find it much easier to react to unwanted product C than to desorb to the main gas flow. So as this resistance increases, our selectivity decreases. Okay, now another consequence of external mass transfer resistances is that we will have a maximum value for the rate that we can achieve in practice. And in order to look at this, let me write the rate of transport as Kx times P over RT x, this S should be here. This is the surface. The X is the molar fraction of species A, and the driving force will be the molar fraction in the main gas flow minus the molar fraction on the surface times a diffusion coefficient, which will be here. Now, we can calculate from classical heat and mass transfer correlations, we can estimate the dependence of Kx with the gas velocity, with temperature, with the diameter of the particle, and with the total pressure in the gas phase. And we may all these parameters will vary within physical reasonable values. We cannot increase the temperature above certain values in practice. We cannot increase the velocity above certain values in practice, or we cannot go to unreasonably high pressures. When we look at the effect of temperature in this mass transfer coefficient, we see that it is small, as we have said before, the activation energy for diffusion is small. Therefore, we may vary temperature and the mass transfer coefficient will not vary much. I want to point out here that we have here reactions involving hydrogen and oxygen, and this Kx varies between 10 to the 20 and 10 to the 21 molecules per square centimeters per second. The effect of particle diameter is much more important, but again, this is particle diameter in centimeters, and we can see that the diffusion, mass transport coefficient varies between 10 to the 20 and 10 to the 21 for several reactions, and the effect of pressure is shown here. And again, we have pressure in torr, so here is about 1 atmosphere. This will be like 10 atmospheres. And this here is about 10 to the 20. This is 10 to the 21 molecules per square centimeter per second. The conclusion is that the maximum rates that we can expect to measure in practice for most gases are in the order of 10 to the 20 molecules per square centimeter per second. And if the reaction involves hydrogen gas, we may reach values of 10 to the 21 molecules per square centimeter per second. So heterogeneous reactions have in practice a maximum value that we can, a maximum rate that we can approach, and that rate will be given by mass transfer and diffusion. I mean, it will be very difficult to find a reaction in which the rate, the rate that we can actually measure will be larger than these values. We can look at an industrial example for a very fast heterogeneous reaction, and that is the oxidation of ammonia to NO. This reaction is carried out in order to make NO, and NO is reacted with water to make nitric acid. The reaction takes place on a platinum rhodium gauze. This is a mesh of small diameter wires, so the reaction occurs only on the external surface. The reason a non-porous catalyst is used is because the reaction rate is so high that the reactant would not be able to diffuse into the pores of a catalyst. So the metal is used in the form of wires in this case. So, and the typical industrial conditions are 10% nitrogen in air, a platinum rhodium gauze, and a throughput of 100 pounds of ammonia per day per ounce of catalyst. If we work these numbers, let me go straight to the bottom line, we find that the rate of reaction is 2.7 times 10 to the 19 molecules per square centimeter per second. That is below the maximum rates that we have said were possible to achieve for a catalytic reaction. Therefore, this is a confirmation that there is we can achieve a rate so not higher than 10 to the 20, 10 to the 21 molecules per square centimeter per second. Now, let me recap at this point what we have seen for external resistances. When we have external resistances, we have that the activation energy will vary with temperature. In the case of a reaction A goes to P, we will see that the rates decrease. The rate decreases as K delta over D increases. So when this factor increases, the rate will decrease. If we have A goes to P goes to C, the selectivity will decrease as the mass transfer resistance increases. So again, mass transfer resistance will make the activation energy of the reaction to vary with temperature, will decrease the observed rates, and will decrease the selectivity of the reaction. Now let's take a look at diffusion and reaction in porous particles when we have a particle with porous with pores in it. Let's go back to the reaction A goes to P, and here what we have is the surface, the catalyst, the surface of the catalyst, the main body of the gas, and the reactant that has to go from the main body of the gas to the surface of the catalyst, then go into the pore, and it will diffuse and react in the pore of the catalyst. If we have a concentration profile for this reaction will look like this. In the main body of the catalyst, we will have a flat concentration profile. Then the concentration or partial pressure of species A will decay along in this film, gas film next to the surface, and then the concentration of A will decrease in the pore, will decay in the pore. Now, we would like to have, in order to fully utilize the catalytic surface, we would like to have a constant concentration here. This decaying concentration reduces the effectiveness of the catalyst because the rate will be smaller as we get into the pore. So here again, if we could reduce this gradient, we will have a more effective use of the catalyst. We may define an effectiveness factor as an observed rate divided the rate if the concentration of A was constant in the pore, and the plot will look as the plots that we have drawn before. The effectiveness factor will decay as a factor that contains, this is L, the length of the pore, times the square root of the reaction rate constant divided the diffusion coefficient. As this increases, the use of the internal surface will decrease, since the effectiveness factor will decrease. Well, let me skip and go straight to what we can do in the lab in order to reduce the effect of mass transfer resistances, or to make sure that we do not have them. And that is page 30. In order to reduce the resistances, we may increase the gas flow rate to reduce the film thickness. The film thickness will in general depend on the gas flow rate. Or we may also reduce pellet size to decrease the pore length. This is what we may do, and this is the simplest approach. In the case, if we have, for example, a reaction in which the catalyst is immersed not in a liquid, but not in a solid, but in a liquid, this will be the so-called slurry phase reaction. We have a reactor, we have a liquid, and we have catalyst particles here. We may increase the rate of agitation, and if we have mass transfer resistances, increasing the rate of agitation will decrease the film thickness around the particles. Therefore, the reaction rate should increase until this film thickness is small. I mean, until this resistance to mass transfer is small compared to the chemical reaction resistance, and then we will have a flat profile. The same thing, we can do the same with a fixed bed reactor by increasing the gas flow rate, and this drawing addresses the same issue, decreasing, as we increase the gas flow rate, the film thickness decreases. A better test, I mean, changing the gas, either the gas flow rate or and the agitation rate has some problems. For example, if we have a reactor and we have a slurry phase reactor and we change the agitation rate, we may have other effects like vortex formation, or if the reaction has a gas, if the reaction is a three-phase reaction, we may have improved gas mixing in the reactor. Therefore, it's not only mass transfer to the catalyst that may change. Other things, other effects may affect the rate of reaction. When we have a fixed bed reactor and we change the gas flow rate, when we vary the gas flow rate, the effect on delta may not be too important, because in the laboratory we cannot change gas flow rates by huge factors. Therefore, we may change gas flow rate, but the film thickness may be insensitive to change in the gas flow rate within the range that we can operate in the lab. Therefore, a better test for mass transfer resistance is the so-called Koros and Nowak test, which looks at the following factors. When there are no mass transfer resistances, the rate of reaction is proportional to the number of active sites per unit volume. If we have a strong external mass transfer resistance, the rate will be independent of the number of sites, because the rate will be dependent only on the coefficient, on the mass transfer coefficient. Remember, if we have a mass transfer control reaction, the rate will depend only on the mass transfer coefficient. When we have a strong pore resistance, the rate is proportional to the square of the number of active sites. Therefore, what these authors proposed was that we should make pellets from with a variety of number of active sites per unit volume. Therefore, we run the reaction with several values of S, and we look at the dependence of the rate on S. If it is proportional to S, we know that there is no mass transfer resistance. If it is independent of S, we know that we have an external mass transfer control. And if it is proportional to the square root of S, we have an internal diffusion controlled reaction. A way to make pellets with different values of S is simply using inert materials to dilute the active material. We can use a pure support, we can use a Poisson catalyst, or we can use a material with the diffusion characteristics close to those of the support. So, summary of what we have said today, we can say that when we have mass transfer with heterogeneous catalytic reactions, we will have a sequence of physical and chemical steps. The step with the larger resistance will be rate controlling. We said that absorption, reaction, and desorption parameters are usually lumped together in a single rate expression. We have seen that mass transfer resistances affect the rate, the activation energy, and the selectivity of chemical reactions. We have also seen that the external resistance put a maximum value to the rate that we can obtain for a chemical reaction. And finally, we mentioned tests for mass transfer resistances in laboratory reactors. So this is all I had to say, and thank you for your attention.
Good morning. Before we continue to look at general relations between thermodynamics and kinetics as applied in particular to catalytic reactions, let me ask whether there is any question on material or on the mechanics of the course, whatever you may have in mind. If not, let's proceed, and let's look again at page 7 and ask ourselves whether these are useful relations. And the answer, yes, they are very useful. Look, for instance, at equation 4. Why is it useful? Because in the vast majority of cases, thermodynamic information is more readily available than kinetic information. Kinetic information may be available for an elementary reaction, say in the forward direction, rate constant in the forward direction. Then if the equilibrium constant is available from thermodynamic tables, then the rate constant for the reverse direction is immediately available. And that's very, very useful information. We shall see toward the end of the lectures that in many cases today, for chain reactions, and it is just getting started now with catalytic reactions, we may have enough information on rate constants of elementary steps to put them all in a program on a computer and calculate rates, yields, selectivity as needed. And frequently we do not have all the information available. We must make some guesses, or we may use this first expression there, the equation 4. Equation 5, is that useful? Yes, it's useful for the same reason. We may have information on the rate of a reaction in the forward direction. And then if it's a two-way reaction or reversible, as we have explained it, then we can also obtain the net rate of the reaction, rate forward minus rate reverse. And it is given by the product of this kinetic quantity, which has been measured already, and a thermodynamic driving force, which is obtained from the free energy of the reaction, which is probably available somewhere in thermodynamic tables. Now, what about the equation 9? Well, that is at the moment not terribly, it doesn't appear to be terribly useful. It says that very near equilibrium, the flux is proportional to the force, like in Ohm's law, or Fick's law, or Fourier's law. These are the linear relations of irreversible thermodynamics. The rate is proportional to the thermodynamic driving force, as given by the affinity, or minus delta G, or G sub I for that particular step, over RT. And is this useful? Well, let's wait until we generalize these three equations that we have for elementary steps to the overall reaction. So far, all we can say is that these are equations, relations, bridges between kinetics and thermodynamics that apply to elementary steps. Okay, so let us then move to the more useful case, general case of a overall reaction, a catalytic cycle that consists of a number of steps, probably more than 2, maybe 10, maybe more. And what can we say about these bridges between kinetics and thermodynamics for the catalytic cycle? Okay, we introduce here a good old workhorse of kinetics. First proposed for chain reactions, then applied to catalytic cycles as well. And it's called somewhat prudently the quasi-steady state approximation. And it says the following, that when you have reached a steady state, the net rate of any step in the sequence, in the catalytic cycle, in the propagation steps of a chain reaction, as shown on equation 10 sub I, that the net rate for any step is equal to the overall rate, net rate of the entire stoichiometric reaction. Equal, and there is a little restriction, within a quantity first introduced now, which is called the stoichiometric number of the step we deal with. And let us immediately find out what that means, stoichiometric number of a step. It is not the same as stoichiometric coefficient. Look at this bellwether reaction, ammonia synthesis. We shall talk at length about it. The stoichiometric coefficients for the overall reaction as we arbitrarily write it. We could have chosen a different way. We could have written 1/2 N2 plus 3/2 H2 is equal to 1 ammonia. But we have decided arbitrarily to write the stoichiometric equation for ammonia synthesis or decomposition the way it's written there, and therefore we have defined the stoichiometric coefficients, which are negative for reactants, positive for the products, and correspond to what you see in the stoichiometric equation for the reaction. This is not what we mean when we talk about stoichiometric numbers. Stoichiometric numbers have a mechanistic meaning. And for instance, if you look at page 10, at the top, you find the stoichiometric numbers for each of the postulated elementary steps that we think are reasonable for representing the way the catalytic cycle turns over. We write every step. It turns out in this case that there are two-way steps. They are reversible in the kinetic sense. And we write them the way we think they occur at the molecular level. And then we ask ourselves, how many times must a given step proceed in such a way that the overall cycle can turn over once. And that how many times is the stoichiometric number for that step. If we multiply each step by the stoichiometric number of that step, and if we sum up all the steps, we reproduce the stoichiometric equation for the reaction the way we have decided to write it. In other words, everything that includes the active intermediates, which are the empty sides and the occupied sides, each side being denoted by an asterisk. They all cancel out, and we end up, when we sum up, with N2 plus 3H2 is equal to 2 NH3. So the stoichiometric number has a mechanistic meaning. The ultimate goal of any mechanistic study in catalytic kinetics is to determine the catalytic cycle, and to write a catalytic cycle we need a lot of background information, chemical intuition, previous knowledge that we gather for the purpose. And it is very rare that we know, as I mentioned today, the